All right. So, implicit differentiation is something that we use when we want to take the derivative of, well, more than one variable in a function or something like that. So let's read through here what we're talking about. So far, most functions that we've seen have been expressed in what we call explicit form. Okay? But then sometimes we also have functions defined implicitly. Okay, so for example, here is a function in implicit form. Okay, implicit because the x's and y's are kind of like mixed together. Okay, that we don't have y solved for in terms of x or solved in terms of x. We just have x and y all mixed together there. So we could rewrite this one though, right? If we were to come across this and you were asked to like take the derivative of it, we might rewrite this in a more clear like explicit form. You know, solving for y. So in other words, what would we do to both sides here to get the y by itself? Divide by x, right? And so we'd end up with y equals 1 over x, or if we really wanted to, because we're going to take the derivative, we can make that x to the negative 1. So it's even easier to take that derivative there. And so without having to take the derivative in implicit form, we rewrite it in explicit form, right? So it's typical. When we take the derivative of something, sometimes we rewrite it into a form we're more comfortable with, and then we take its derivative, and so we'll end up with, you know, dy dx equals negative x to the negative 2. Very good. Yeah, be careful, right, with those negative exponents. When you subtract a power, you go down, you know, our negative exponents actually kind of go up in the number. But anyway, okay. So negative 1 minus 1 is negative 2. It is not always possible, however, to solve for y explicitly. So for example, this right here, right? It's got x's and y's mixed together, and to get the y by itself, right? So we could solve this for y, but even if we solve this for y, we would end up with still like x's and y's kind of mixed together on one side, okay? And so we can't just like give up, okay, at this point. We can actually proceed from here and take the derivative as it's currently written, okay? And we're going to use something called implicit differentiation. Okay, so some keys to finding the derivative, the first derivative, dy dx implicitly, is to understand that differentiation, we've always been doing it with respect to x, right? Or with respect to whatever our independent variable was, right? So if we had like t or, you know, whatever other a's sometimes, right? It would always be with respect to the t or respect to the a. And so here, when we take the derivative, we're doing it with respect to x. Okay, so when you differentiate terms that involve x alone, you differentiate as usual. Okay, but when you differentiate terms that involve y, we have to apply the chain rule. Okay, so let me show you what I mean by that. And here we'll do it with this one. Okay, so I'm going to show it to you kind of a little bit more step by step. I know this is a super simple derivative. Everyone knows the answer here is going to be 3x squared. But let me show you just one little extra bit here, right? When we see x to the third power, okay, when we take the derivative of that with respect to x, we can use the chain rule here, right? This is like something being cubed. And we know that the derivative of something cubed is 3 times that something to the second. And then applying the chain rule, we have to multiply by the derivative of what's inside. Okay, what's inside the cube here? An x, right? And so what is the derivative of x? 1, right? And so we never write this times 1 on the outside, but we could, right? Anytime we're taking the derivative of x squared, you know, we could say, okay, well, that's going to be something squared is 2 times that something to the 1 times the derivative of what's inside. Again, what was inside here is the x. I'm going to write it in a slightly different fashion, though. The derivative of x with respect to x, right? Isn't that what that is? We're multiplying by the derivative of what's inside. Right? And so I know this notation is confusing, but just, you know, think of it. The derivative of x with respect to x is the same thing as saying dx over dx like that. Of course, when you have the same thing on the top and the bottom, it cancels out and simplifies to 1, so this is really just saying 3x squared times 1 there. Right? We're multiplying by the derivative of what's inside. Same thing here. If I take the derivative of x squared, or something squared, it's 2 times that something to the 1, times the derivative of what's inside. The derivative of x with respect to x. But we always know that's going to be 2x to the 1 times 1, so it's just 2x to the 1, right? And here it's just 3x squared, right? Super simple, typical kind of stuff. We don't write this because it's just silly to write this. But now that we're going to be mixing up x's and y's, and when we go to multiply by the derivative of what's inside, sometimes these this won't cancel out, right, if we have a y up there. So let's take a look at this one, all right? So when I go to take the derivative here of y to the fourth, we can apply the chain rule to it too. Okay, what's the derivative of something to the fourth power? 4 times that something to the third times the derivative of what's inside. Okay, what is the derivative of y, or how could we write that? dy over dx. Okay, dy over dx. So we have to apply the chain rule there because y, when we take the derivative of the inside piece, it ends up being dy dx, right? We don't have the derivative of y, so it's dy dx. Okay. What's the derivative of minus 5x? Yeah, minus 5. Okay. If you want to, again, if we could leave it and say, okay, it's minus 5, and then the derivative of x with respect to x is, dx over dx. If you really want to put that in there, use the chain rule, and then, of course the derivative of 3 is plus 0. And so, again, the final derivative here is 4y cubed dy over dx minus dx over dx is just 1, so it's 5. Okay? And we have to kind of leave this as it is, right? We don't really have, a way to simplify this anymore, so we'll just say that's our derivative. Okay? And here was our derivative, and here was our derivative. So this is a chain application of the chain rule. So this is why we don't really bring it up earlier on. We really needed that chain rule to kind of show what was going on here. And so, technically I could have been writing these dx over dx's every time we took the derivative, but that might have been a little more confusing for you guys because we didn't have the chain rule already. So, didn't want to put the cart before the horse, so to speak. Let's take a look at letter C here. Okay? Now, we want to be careful here. We are differentiating here with respect to what variable? T. And so that means when I differentiate x and I differentiate y, okay, it's going to be dx dt, dy dt. Okay? Here it was x and x, so we could just, simplify real nicely here. Here it had some y's and x's mixed together, but the derivative of y with respect to x was dy dx. The derivative of x with respect to x, that's implied to dx dx. But here it's dt. And so we want to be really careful here. This is on purpose, not a typo. All right? So the derivative of cosine of something is negative sine of that something times the derivative of what's inside. What is the derivative of x with respect to t? dx dt. Okay, plus the derivative of 3e to the something is, bless you, 3e to that something again, times the derivative of what's inside. So inside the e function is y. And what's the derivative of y with respect to t? dy over dt. Okay? And so there is our derivative with respect to t of that function right there. Actually, maybe I shouldn't call it a function. The derivative of that expression right there with respect to t. I don't necessarily know it's a function off the top of my head. Okay? Easy peasy here. All right, now this next one, we have a's and b's, okay? So this can get even more tricky because now we're mixing up, x, no more x's and y's, it's a's and b's. So derivative of a, okay? And here we have a and b squared. When I go to take the derivative of this, what rule are we going to need to use? Yes, okay? So something as innocuous looking as this, it's just ab squared. Its derivative should be so easy. It's a product rule, okay? Because we have two things multiplied together here, a and b squared. Okay. Mr. Widmeyer, you had two things multiplied together here, the 3e to the y. You're right. And we could have used a product rule there, but since that 3 is just a coefficient, we can just bring it along, okay? And just take the derivative of e to the y and dy dt there, okay? But here, it's two functions, and so when we take the derivative of those two functions, we have to use a product rule, okay? So, we'll do the second here, b squared times the derivative of the first. What is the derivative of a with respect to a going to be? Just 1, right? If you want to, you can rewrite that as the derivative of a with respect to a. You can write it as, da over da, dA over dA. But that's going to simplify to 1. Plus the first times the derivative of the second. What is the derivative of something squared? 2 times that something times the derivative of what's inside. What is the derivative of b with respect to a? dB over dA. Okay, and then simplifying here, again, that's just a 1. And so we end up with b squared plus a times 2b times dB over dA. And that's our derivative. Okay? That's our derivative. So watch out. Product rule in there. Okay? Questions on any of that? Questions on any of that before we move on here? Okay. No? We're good? Okay. Flip to the next page there. Okay. So, guidelines for implicit differentiation. Okay. So the first step there. So when we go to implicitly differentiate in an equation setting. Okay. So this is like for an equation. Those earlier problems we did, they were just expressions, right? They didn't have an equal sign. Those were just expressions. But these are equations, right? We're going to have equal signs in our functions or our problems now. Step 1, differentiate both sides of the equation with respect to x. Okay? We technically already do this, but sometimes you just kind of take it for granted. All right? Right? If I have like, again, if I have like y equals, again, just something simple like x squared. Okay? This is an equation, and when we take its derivative, yes, we take the derivative of the x squared, but don't we also take the derivative of y with respect to x there, right? Because what do we write in the place of y? We write dy dx, don't we? The derivative of y with respect to x is, and then the derivative of x squared is 2x. Okay? So we do that already, but now when we come down to equations like this, okay, we don't have it written nice and neatly with y equals stuff with x. We're going to have stuff over here. We're going to have stuff over here. And so we differentiate. We want to do the same thing to both sides. Okay, differentiate both sides. Okay. And one other little thing here with respect to x, and of course this is understood, so it doesn't always, it's not always x. It's just kind of like whichever variable is requested. Okay. So understand, typically, right, x and y, those are like our bread and butter variables. We use those all the time. But, every once in a while it could be t's or, a's or b's, whatever. So just keep in mind, be really careful about how you read these, okay? We get so used to our eyes seeing dy dx that then later if we're asked to find dx dy, this can kind of throw us off a little bit. So just be careful there, right? Things get changed around. So watch your orders and stuff like that. So then, once we've taken the derivative, then we'll collect all the terms involving dy dx to one side of the equation. It doesn't have to be the left side, whatever side you care about, left or right, doesn't matter. And then move all the other terms that don't have a dy dx to the other side of the equation. Okay? And then factor out a dy dx on that side and then divide to solve. Okay? So we'll run through this problem right here. Okay, so for example 2, we want to find dy dx given that y cubed plus y squared minus 5y minus x squared equals negative 4. Okay, so obviously we cannot rewrite that explicitly, right? We can't solve this for y on our own. If you wanted to rewrite it some, you could. It's up to you. But we can also just take the derivative right as it's written. Okay, in the first situation here, we want to find dy over dx. So we're taking the derivative of y with respect to x. So when I go to take the derivative of y cubed with respect to x, what will that be? 3y squared times dy dx. And again, why is that? Because we're taking the derivative of something cubed. The derivative of something cubed is 3 times that something to the second times the derivative of what's inside, in this case with respect to x. So the derivative of y is dy over dx. Okay? So that y cubed becomes that right there. Okay? Plus y squared. So now we're going to do a plus. And what's the derivative of something squared? 2 times that something to the 1 times the derivative of what's inside. What's the derivative of y? dy over dx. Okay, and so there's what y squared becomes. Okay, and then let's take the derivative of minus 5y. So minus 5, that's just a coefficient. What's the derivative of y with respect to x? dy dx, right? So y just becomes a dy dx. Minus, what's the derivative of x squared with respect to x? 2x. That's an easy one, right? Again, if you want, you can write times dx dx, right? Dx over dx, but that's just going to simplify to 1 here. Since we're taking the derivative of x squared with respect to x, you don't have to, it's just going to be dx over dx. Equals, and what's the derivative of negative 4 with respect to x? 0. Okay, easy one. Easy peasy. Okay, I didn't leave myself much space, but oh well, that's okay. For my other, because we've got to do the other derivative there. All right, so we've taken the derivative. We've taken the derivative, but now we want to actually see what is dy dx. What is the derivative here, right? We have a bunch of dy dx's. And so again, if we go through our guidelines, we differentiated both sides with respect to x in this case. Now we want to collect all the terms involving dy dx to one side. Now, I think it's pretty obvious here we want to keep them all on the left side, right? Because they're all there already. We just got to move that minus 2x that doesn't have a dy dx over to the other side. So let's use a little bit of algebra here. And proceed like so. All right, so I just added 2x to both sides. And now to solve for dy dx, to get the dy dx by itself, to get that derivative by itself, what should we do now to these three terms? Factor, right? They all have a dy dx in common, so we can factor that out. Okay. We're not going to worry. If there was some other GCF here, we're going to leave that be. Okay, so I would not, if there was some other thing you could factor out besides the dy dx, I would not factor that out. We're just trying to get dy dx by itself here. So we'll leave everything else inside the parentheses. Okay, this is not a GCF situation. We just want to get things over. Okay. Okay. So this is dy dx times 3y squared plus 2y minus 5. Okay, dy dx times 3y squared plus 2y minus 5. This is not saying take the derivative of this thing with respect to x, right? To say take the derivative of this with respect to x, you would write d dx times of the 3y squared plus 2y minus 5, right? That's how we say take the derivative of this thing with respect to x. This is dy dx, the derivative, okay? dy there, dx, so anyway. So I'll get there. All right, last step here, what should we do? To get dy dx by itself? Divide. So it's going to be 2x all over 3y squared plus 2y minus 5. And there is our derivative. Okay, there's the derivative. Implicitly defined as well. Oh, maybe that's explicitly defined. I don't know. At least we got the dy dx by itself at least. Okay, so in this situation, we were actually able to solve for dy dx. Okay. Questions on any of that? All right. So now let's look at it in the other less comfortable way, right? So we did dy dx. That's what we're used to. Okay. But now let's look at it. Just because now we can think about in these terms taking the derivative with respect to other variables. Let's take the derivative here with respect to y now and see how things change. Okay, so let's take the derivative of that original function there with respect to y. Okay, so this will be dx over dy now. See how things change. Okay. So now, y cubed, well, we take the derivative as we normally would. What's the derivative of something cubed? 3 times that something to the second times the derivative of what's inside. What is the derivative of y with respect to y? 1, right? If you want, you could write dy over dy, but I'm just going to put a 1 there. Okay? Plus, what's the derivative of something squared? 2 times that something to the first, or I'll put the 1 up there showing up. And then times the derivative of what's inside. What's the derivative of y with respect to y? It's just going to be 1, right? Okay. Minus, what's the derivative of 5y going to be with respect to y? Just minus 5. Okay. So if you look at this, we're taking the derivative with respect to y, and so taking the derivative of y cubed, y squared, and minus 5y is like we would expect it to be. 3y squared, 2y minus 5, right? It's like you're treating the y's like the x's now. But now we have an x squared we're going to run across here. We're going to have to treat it like we used to treat the y's, right? So when we go to take the derivative here, it'll be minus 2x to the 1. Okay, because again, the derivative of something squared is 2 times that something to the 1 times the derivative of what's inside. What is the derivative of x with respect to y? Dx dy, right? We don't have an expression for that, so we're just going to rewrite the dx dy. Okay, equals 0. And then Sean, you have a question?
So could we bring the 2x to the other side just like before we did anything?
Absolutely. If you wanted to, yep, absolutely. You can manipulate things algebraically however you want prior to doing the work there. So in this case, we're going to end up doing that anyway, right? Now we're going to have to do it. We have to get the, I'm going to go ahead and take the negative 2x times dx dy. I'm going to move it over to the right-hand side, okay? Again, if you always want to like stick to something, the same step every time, you can feel free to just leave this on the left-hand side and move these 1, 2, 3 terms over. Okay, so if that's more your comfort level, if you just prefer to take all of these terms that don't have a dx dy over to the right-hand side and leave this on the left-hand side, that's fine. Okay, but of course we can just move this single term over. It's really going to end up being the same thing. So I'm just going to move the single term over and make it 2x dx dy. And so we added 2x dx dy to both sides there. And then for our final step, divide both sides by 2x, right? And so we end up with dx over dy equals 3y squared plus 2y minus 5 over 2x. Okay. Anyone see anything special here? Yeah, Bryce? It's the reciprocal, right? And which should make sense here, right? If we have dy over dx equals that, then the reciprocal of dy over dx over dy had better be the reciprocal. You're not impressed. Yeah. All right, well, that's fine. It is Monday morning, I guess. So anyway, moving on. All right. So anyway, you're probably more mad than impressed because you're like, why'd we do all that work? I understand. Anyway, all right. So number 3, find all points of horizontal and vertical tangencies for the graph of x squared plus y squared equals 1. Now, you actually can do this mentally here. Y'all can do this mentally, I think, because x squared plus y squared plus 1, what is that? It's a circle centered at the origin with radius 1, right? Remember, the 1 is, that's r squared there, but if it's a 1, the square root of 1 is still 1. So think about a circle centered at the origin with radius of 1. If we're looking for horizontal tangencies, okay, well, let's maybe draw a picture here to help ourselves out. I draw a very ugly circle here, and I apologize. Actually, it's not that bad. Okay. What will the locations of the points be for horizontal tangencies on our circle here? 0, 1. There's 1, right? There's 1. 0, 1. That's going to be a horizontal tangent line if I ever saw one. All right. And what, anywhere else? 0, negative 1 as well, right? If I ever saw one. Okay. What about vertical tangencies? Where do we think those will exist? 1, 0. Yeah, very good. Again, vertical tangencies. And then we have any more? Negative 1, 0. All right, so we already know the answer for this. We already know the answer. But let's do it and see if the math backs it up here. So why don't you guys go ahead. I'm going to give you the opportunity. Take the derivative of this, okay, with respect to x. Okay, so take the derivative of this with respect to x. Implicitly, please. Implicitly. Could you potentially rewrite it explicitly and take the derivative? Yeah, I think. But take the derivative implicitly here. So find dy dx. Go ahead, take like a minute. Find dy dx. Okay, and I'll kind of come around and see if you need any help with that. And then we'll move from there. this under the rate. Good. What's the derivative of what's the derivative of 1? That's equal to 1. But the derivative of 1 should be 0. Okay, good. Now you have did the dy dx by itself. Good. You can simplify the terms on 1, 2 there. What is the derivative of 1?
35.
Yeah. Again, common mistake.
It's going to be a long week.
Good. You can, oh, here, you took the derivative of with respect to x, dy, d. Or, hang on a second. No, you're right. No, you're right. Okay, sorry. You can simplify the 2's.
It's TJ Carter. They've lost my results in my it's
Oh, I see. Okay, I was like, I was confused with the bottom. Okay, sorry, brain fart there. Okay, so this is good, except what's the derivative of 1? It should be 0. So, hey, I'll be back. You don't want to divide both sides by 2x plus 1y. 2y is being multiplied by dy dx. So if you want to isolate dy dx, you would subtract both of the terms first. You see it?
We're down the street.
Good. Are there people that are interested in adding people? No, there's actually today doing like this.
It's going to be the same thing I did with the bio. We added like a big water class. Really stuff to everybody's here. I mean, I won't let anybody do that, but I'm sure maybe correctly should be greasy.
The derivative is negative x over y. Okay? So, how are we supposed to use this? We know what our answers are, right? We know where the horizontal tangencies, where the vertical tangencies are. But let's say we weren't able to figure that out, kind of mentally here, right? How can we then use this to figure out where we have a horizontal tangent? What should we do with our derivative? Set it equal to 0, right? Because a horizontal tangent is when our derivative is 0, right? A horizontal tangent has a slope of 0, so we know when our slope is 0. So we set negative x, okay, over y equal to 0. When does a fraction equal 0? When the numerator is 0. So this is just really we need to figure out when negative x equals 0, or in other words, x is 0. Okay, so far so good. We've got x equals 0. And sure enough, where we had those horizontal tangencies, does x equal 0 at those points? Yeah, right? X equals 0, x equals 0. But then how can we find their matching y coordinates? What should we do? Plug it back into the original. Plug it back into the, bless you, original. So 0 squared plus y squared equals 1. 0 squared is 0. We get y squared equals 1. When we square root both sides there, we end up with y equals plus or minus 1. Oh my gosh, there are the 2 points. 0, 1, and 0, negative 1. Okay, horizontal tangents. Okay? If we want to find vertical tangents, that's when our derivative would be what? Undefined. When is a fraction undefined? When our denominator is 0. So we'll set y equal to 0. Oh, look at that. 0 y coordinates. Okay? And then we'll find the matching x coordinates by plugging back into the original function. So it'll be x squared now plus 0 squared equals 1. So we get x squared equals 1, bless you. And so we get x equals plus or minus 1. And so we get 1, 0, and negative 1, 0. Okay, and there are our vertical tangents. Okay, just like that. Okay. Questions on any of that? Questions on any of that? All right. Let's take a look then at example 4 here. We're going to do these next two, and then that's it. Okay, we'll be done after these next two. Okay? So, determine the slope of the tangent line, that is, doing what? Slope of the tangent line, we're supposed to take the derivative to the graph of this function. Okay? At the point root 2, comma, negative 1 over root 2. Okay, so take a minute, examine this equation here that we want to, derive or take its derivative. We want to differentiate. Okay. So drink it in there a little bit. All right, looking at it very carefully. What additional, complication are we going to have when we go to take this derivative here? What's that? There's a product rule. What? Where? Minus x times y. That little simple looking little, product right there, that's a product rule we need to do. X times y is a product of two functions, right? X and y. Okay? So we'll have to take the derivative there using the product rule of that part. So we'll proceed as normal here. The derivative of x squared with respect to x, right? So it's going to be 2x, all right, plus the derivative of 4y squared is going to be 8y times dy over dx. Okay? So again, using that chain rule, right? The derivative for x squared. The derivative of something squared is 2 times that something times the derivative of what's inside, in this case with respect to x. The derivative of x with respect to x is 1. 4y squared's derivative, the derivative of something to the second is 2 times that something to the first. So 2 times 4 is 8, and then times the y. Times the derivative of what's inside. What's the derivative of y with respect to x? dy dx, right? So there that is. The derivative of 3, 0, minus, and then parenthesis. Don't forget the parenthesis. That minus, it's going to be subtracting the entire quantity of the product rule there. Don't forget that parenthesis. Don't forget that parenthesis. Okay? It's minus the entire quantity of the product rule. If you want to kind of help yourself here, you could rewrite minus xy as plus negative xy if you wanted to. And in that case, then, you would take the derivative of negative x times positive y there. And that would kind of alleviate that, potential where you're going to have to make sure that minus is in front of parentheses, bless you. Okay, that would take care of that. So it's really up to you how you want to do that. But just be careful when there's a minus in front of a product like that. It's minus the quantity. And so when you do the product rule, it's minus the quantity of the product rule there. Okay, but again, if you make it plus a negative, that will fix it. And you can just, do negative x times y. So either way will work. All right, so I'm going to treat it like it's the minus xy, though, because that's what I started with. Okay, and I can't erase pen, sadly. All right, not these pens at least. So we'll do the second, y, times the derivative of the first, so the derivative of x, 1, plus the first, x, times the derivative of the second. And the derivative of y with respect to x is just dy dx. Just dy dx. Okay, just dy dx. If you want to think about it in terms of a chain rule, y by itself is really y to the 1. So its derivative would be 1y to the 0 times the derivative of what's inside, dy over dx. Of course, anything to the 0 power is 1, so it's 1 times dy dx. So it's just dy dx. The derivative of y to the 1 is just going to be dy dx there. Okay? And so then if I just equals negative y minus x dy over dx, like that. Okay? Okay. Now, at this point you have some options. If we were asked to find dy dx, right? Or if we were asked to, find some particular slopes or something like that, or find when we had those particular slopes, we would probably want to solve for dy dx here, or solve for dy dx here like we did there. But in this case, I don't need to isolate the dy dx, or at least I don't need to isolate the dy dx yet. But let's go ahead and do it. Let's just go ahead and do it because that's what we've been doing, right? So let's get all those, let's collect those dy dx terms together. I'm going to add the x dy dx over, subtract the 2x over. So I'll end up with 8y dy over dx plus x dy over dx equals, and then negative y minus 2x. Okay, so we'll go about the way we did it earlier, right? Collecting all of our dy dx terms to one side, moving everything without a dy dx term to the other side. Now we'll factor out that dy over dx. Okay, and end up with dy over dx equals negative y minus 2x over 8y plus x. So there's our derivative. Are we done? No. What do we still have to do? Plug in our point. Okay? And now here, right, here is kind of not an answer to a question, but like in the past, right, when we've been given a point to evaluate our derivative, or to evaluate, our derivative at that point, we only have been using the x-coordinate, right? Because our derivatives up to this point had only had x's in them. But now our derivatives have both x's and y's mixed together. And so we're going to use the root 2 and the negative 1 over root 2, right? The root 2 goes in wherever you have an x. The negative 1 over root 2 goes wherever you have a y. And so the derivative here of y with respect to x evaluated, remember that's how we write that, at, I'm going to just include the point there, root 2 comma negative 1 over root 2. Okay, so this is like an easy way to write that, or we're plugging in that point, equals, so then it'll be negative 1 over root 2 minus 2 times root 2 over 8 times negative 1 over root 2 plus root 2. Okay. Are we done now? Did we find the slope of the tangent line to the graph at this particular point? Yes. Do we need to simplify this any further? No. It's all arithmetic. If it's a free response question, you're done. Okay, if it's a free response question, you're done. Okay. Questions on any of that? Okay. So there it is. That's the slope. Okay. That's the slope there. You don't need to proceed any further. All right. Let's move on here then to number 5. All right. So here we want to determine the slope of the normal line. Now, I don't think we've talked about the normal line, have we? We haven't talked about the normal line yet, right? So don't freak out. It's super simple. The normal line, the slope of the normal line, I should say it this way. The slope of the normal line is the perpendicular slope of the tangent line. How easy is that? Okay? To determine the slope of the normal line of a function at a specific point, it's just the perpendicular slope of the tangent line. That's all it is. Okay? So from here on out, if you're asked to find the slope of the normal line, you do the normal stuff, you do the typical stuff that you do to find the slope of the tangent line, and then, well, you have the one additional step of then getting the perpendicular slope. Okay? Now, when we go to take the derivative here, what rules are we going to have to employ to help us out when we go to take the derivative of this implicitly? Chain and product. Yes. Chain rule, because we have stuff being squared there, right? Of course, if you wanted to, you could absolutely square out that x squared plus y squared to the second. Debatable about whether that's easier or not, because then you're going to create like product rule in there for yourself too. And then here a product rule, because it's 100x y, little x times y next to each other. That's a product rule. Okay? So, let's take the derivative of this thing. All right, I'm going to rewrite it here just so I can like refer easily to it. Okay, so let's take the derivative of the left-hand side here. Again, we're doing it with respect to x. With respect to x. Okay, it doesn't say, so we're just assuming it's with respect to x. Okay, so the 3, it's a coefficient. We can just leave that out front. So we take the derivative here of something squared. Our outermost layer here is something being squared. So what's the derivative of something squared? 2 times that something, so 2 times the 3 that's already there is going to give us 6. Parentheses, leave what's inside to the first. If you want to write a little 1 there, that's fine. You don't have to, of course. It's understood if you don't write it. Times the derivative of what's inside, right? So the derivative of what's inside, I'm going to use parentheses here. The derivative of x squared with respect to x, 2x. The derivative of y squared with respect to x, 2y times dy over dx. Okay. So then we did the derivative of something squared. It was 2 times that something to the 1, leaving what's inside alone, times the derivative of what's inside, 2x plus 2y dy dx. Equals. So that was the left-hand side. Any questions on just the left-hand side alone there? We're all good on the left-hand side? Yeah, Sean?
Parentheses are required or last part.
Yeah, because if you don't put them there, right, so let's imagine if they're not there. Well, maybe I'll put it up like here. You see what the issue would be? Okay, and that for some of you on your quizzes too, if you notice, I maybe drew in some parentheses in some locations. Again, I know what you mean, but just be careful because I don't, should we get into more calculation stuff like that, I don't want you to mess up. But we can see here that we need the parentheses around this quantity because otherwise it's just the 2x that gets multiplied with this when really it should be the entire quantity that's being multiplied there. Okay. When you use the chain rule, it's times the derivative of what's inside. That means the entire quantity of the derivative of what's inside. So you want to put the parentheses around there. All right, equals. For the product rule here, I'm going to consider the 100x to be my first function and then y to be the second. Okay, just to make it easier. So I don't have to worry about distributing the 100. I'll just make the 100 go with x. So it's going to be the second times the derivative of the first. What's the derivative of 100x with respect to x? 100 plus the first 100x times the derivative of the second. What's the derivative of y with respect to x? dy over dx. Okay. Question?
Would it be okay if we left the 100 out of the parentheses and put that
Yep. So if you have like that, yes, that's absolutely fine. Yeah. I just liked, yeah, that's fine. No problem. As long as you don't forget the parentheses, that's fine. Okay. All right. Now what should we do at this point? Yeah. So ordinarily at this point, what we would do is try and get all the dy dx terms to one side and all of the non-dy dx terms to the other side. But that's going to get a little messy over here because we have like x squared plus y squared times the quantity 2x plus 2y dy dx. So it's like a binomial times a binomial there. So we have to actually multiply this out first, like using FOIL and stuff, right? And then distribute the 6, and then we can start moving things around. Ugh. But what are we really trying to do here? It doesn't necessarily say find dy dx. We just want to find what the slope of the normal line will be at the point 3,1. I've got the derivative here in front of me. It's just not solve for dy dx. But isn't this just, it's the derivative still, it's just not solve for dy dx. But I can take this 3, and where can I put it in here? And all the x's. And this 1, where can I put it in here? All the y's. And so if I'm just trying to find a particular value, I can evaluate this at the point 3,1 before I start trying to get that dy dx by itself. Okay, so it saves us a little bit of headache here, okay, for a Monday morning. And so I'll go ahead and plug these things in. Okay, and again, I'll take a lot of steps here just to show this, just so you can see what we did. Okay, so wherever there's an x3, wherever there's a y, put in a 1. And so let's see here, we'll get 9 plus 1, so 10 times 6, that's going to give us 60 times, and then here, 2 times 3 is 6 plus, ooh, it's 2 times dy dx, so be careful there. So it'll be 6 plus 2 dy over dx. Okay, that's 6 right here, and that 2 right here, they can't add, right? So be careful right here, right? 6 plus 2, you can't add them together because it's 2 dy dx. All right, they're not like terms, so don't put them together. It's a 6 plus a 2 dy dx equals 100. Same thing here. This 100 plus this 300, they can't go together because there's a dy dx with a 300 there. So you have to, only combine like terms. Okay. And I guess I should take one more step here. Make this 360 plus 120 dy over dx equals 100 plus 300 dy over dx. Isn't this a lot easier than it probably would have been? I think so, right? I think so at least. So now what should we do? How should we proceed from here? We want to find our slope. So what do we need to do? Now is when we want to solve for dy dx. Now we want to isolate the dy dx together, right? We only have, it's so much easier, so many fewer terms. So I'm going to subtract the 100 over to this side, make it 260. Subtract the 120 over to this side, so it's 180. Okay. So again, collect the non-dy dx terms together, collect the dy dx terms together on the other side, and then we'll finish by dividing both sides by 180. So you get dy over dx equals 260 over 180, which is 26 over 18, which is 13 over 9. Okay. And so our slope of the tangent line is 13/9. So therefore the slope of the normal line will be negative 9/13. And that is our final answer there, right? That's our final answer. Be careful with that, right? It's awfully tempting because 90% of the time we're finding the slope of the tangent line. So it's awfully tempting to do all that work and think, I'm done, yay! But then you have to find that normal line slope. It's perpendicular, okay? So be careful. If this were a multiple choice, I can almost guarantee you would see 13/9, as one of your possible answers because it's a common mistake. All right? Questions on any of that? All right, so let me get you guys an opportunity to get started. This is not trivial, so please take advantage of the time I'm giving you here to get started on things so you can kind of iron out any sort of confusions or questions. We're going to spend another day on this tomorrow. Okay.
Please go to the bathroom.
Yes.
Thank you.
Okay, I just posted it to the Google Classroom, okay? So it's section 3.5, 4, 7, 13, 16, 27 to 37 the odds, and then 98. Yes?
I have a question on the notes.
All right, I'll be right with you one second. Let me just finish this real quick.